Good morning. Last couple of classes we looked at one heat treatment process that is called precipitation hardening, and in this particular case what we saw that if you have a terminal solid solution and in that case heat the alloy to a temperature where its structure it is homogeneous, it is a single phase, and then you quench it, and when you cool it to room temperature, what you do, you suppress the precipitation process, and subsequently you find if you leave it at room temperature for some time or let it age at room temperature, or maybe you let it age or to enhance that aging you heat it to a little higher temperature, then what happens, very fine precipitates form, and these precipitates are so fine that they cannot be seen under optical microscope. But as a result of this process, as a result of this transformation that takes place in that supersaturated solid solution, its strength increases, and we looked at it at some detail. And today we begin a new chapter that is called heat treatment of steel. And steel, that physical concept already introduced, we looked at its phase diagram, and we also know that by changing the composition you can get varieties of steel, varieties of properties, and we will now see by giving heat treatment how the structure can be modified. So, what we are going to look at under this in the next maybe 6 to 8 classes is we will revise, look back something which has already been covered, just so that you are able to follow this lecture. We talked about phase diagram, we talked about time temperature transformation diagram. We will see that in this time temperature diagrams there are 3 distinct regions. You can and basically you can say that you can get 3 distinct type of properties or microstructural feature. Say one is a pearlite, another is a martensite, and in between you get bainite type of structure. We will look at how the isothermal kinetics of that process, and any heat treatment that you do. Say if you have a steel at a room temperature and you have to give it a heat treatment, you will find like in a solid precipitation hardening, you heat it to a temperature. So, that means you take it to a temperature where steel transforms to its high temperature crystallographic form, that is austenite, and this process is called austenization. We will look at is process of austenization and what are the factors what determines that process of austenization, and how long should you heat a sample at a particular temperature, so that it becomes fully uniform or homogeneous austenite. We will also look at effect of alloy elements on time temperature transformation diagram and phase diagram. And very often what we do, this is called time temperature transformation diagram, and these are drawn under isothermal conditions. These plots or these diagrams are generated from experiments conducted under isothermal condition, but normally when you cool a steel, when you quench at a temperature at a particular point in the steel changes continuously. Now, we will see that what is continuous cooling transformation diagram. Is there a relationship between CCT and TTT diagram? Then we will look at few commercial heat treatment, very common heat treatment processes: annealing, normalizing, hardening and tempering, and we will also look at hardening. Now, coming back, it may be worthwhile to look at one basic difference between precipitation hardening and the hardening treatment that we are going to talk about in steel. Now, in precipitation hardening, when you heat a metal to a high temperature then quench it rapidly, what happens? You are trying to keep excess amount of solute in the lattice. So, your solid solution strengthening may be there to some extent, but your lattice is not distorted very much, or your actual strength does not increase. So, the quenched material may show the lower hardness than the structure which you had initially. Initially, you may have a two phase structure, you take it to a single phase region, quench it very fast, you are retaining more amount of solute elements. So, normally one would expect that since you have more solute, it should be harder, but it is not so. You find that hardness decreases, but when you age, you form a very fine precipitate all through the matrix, and which gives it high strengthening. Or now, the situation is little different in case of a steel. When you quench, what happens? You heat it to a stage where that ferrite, normally at room temperature, steel is made up of, let us say, ferrite and cementite. When you heat it to austenite temperature, that cementite or carbide dissolves in the matrix, you have a single phase structure, and when you quench, you retain high amount of carbon, no doubt. And but we will see in this case, unlike precipitation hardening, instead of strength going down, strength goes up substantially, and we will try and see why this happens. And in fact, the reason lies within the transformation processes that take place in the steel during the heat treatment process. And we recall a part of this here, what we have drawn is a part of the phase diagram, that is iron cementite metastable phase diagram. Now, why we have drawn a part? Because most of the time, say you have a steel, say suppose you have a 0.8% carbon steel. Let us first consider the process of heat treatment with reference to this particular steel, and when you, this steel is called eutectoid steel, and when you heat it to the austenitic region, what happens? You get homogeneous austenite. If you leave it at this temperature, above this temperature called the eutectoid temperature, which is around 723 degrees centigrade, and if you heat it little above 30 to 40 degrees centigrade above, in that case it will become homogeneous austenite within a reasonable span of time. And now we will try to see what happens to the structure, what type of structure will it develop if you cool it under different conditions. And if you recollect this earlier diagram, this particular steel is known as eutectoid steel. This particular steel is known as eutectoid steel, and if you remember that structure, it is when you cool this steel. So, what happens is you have pearlite forming, and pearlite is made up of alternate layers of cementite and ferrite. So, this is the way this pearlite forms. So, this is a nodule of pearlite. In that way, you will find number of these nodules they develop. So, when a cementite plate develops here, it can also develop in the austenite grain on the other side also. So, basically what happens, and this growth both will grow parallelly. So, within one grain you may find there will be several nodules of pearlite, which are made up of alternate layers of cementite. Usually in the microstructure, what we see, that normal microstructure, when you see in steel, you etch with nital. In that case, the cementite, it etches the boundary, but the cementite plate is so fine that it appears as a dark line. So, it will be 100%, this will be 100% pearlite. So, 100% pearlite, and which is made up of around roughly 14% cementite and rest balance ferrite. So, you will see that plate thickness of cementite, they will be 1:7 around. Whereas, if you have a steel on this side which is known as hypoeutectoid steel, and here the structure will be, there will be some primary or we will say that this is called proeutectoid ferrite. So, ferrite which precipitates or forms, initially it may form on the grain boundaries and they grow. These are the ferrite grains, and balance will convert into, once it reaches this temperature, balance of this will convert into Pearlitic structure. So, the structure here will be made up of proeutectoid ferrite and pearlite, and this pearlite essentially again will be made up of cementite plus ferrite. So, in fact, amount of this proeutectoid ferrite, this will be maximum at this end, and as you approach this eutectoid, amount of proeutectoid ferrite goes on decreasing. Now, same thing happens, similar thing happens here. What you have when you cool, this is called hypereutectoid steel, and when you cool from this austenitic region, initially this proeutectoid cementite will form, and this cementite, when it forms, you will find they will form along the grain boundary first, and they often form a thin film around the grain boundary, because these are the likely places. And in fact, and when it grows, you can clearly see, because normal nitrile etching, it etches only the boundary between cementite and austenite, or cementite and ferrite. So, you may find that there are the white, this type of a network, bright white network around this, and balance will be, this portion will be pearlite. But interesting thing which you will find in hypereutectoid steel, because of this composition nature, here the amount of ferrite increases from let us say 0% over here at 0.2 to around 100% to close to 0.02 carbon. But in this case, amount of this proeutectoid cementite, this will be proportional to this portion only, this over that entire, and that means this portion is x proeutectoid cementite, and this will depend on, this is 6.67 is the amount of carbon in cementite, somewhere in this end 6 point minus 0.8. Now, this is much larger. So, amount of proeutectoid cementite which you can have in steel is very less in fact, and that is why you will have only, you can only expect a very thin network of cementite, and cementite is very brittle, and this type of structure, therefore, a brittle network at grain boundary is unwanted, and all heat treatment process we have to see that we do not let this happen. And we know, you must recollect that crystal structure of austenite, this is face centered cubic, it has 4 atoms per unit cell, whereas in BCC it has 2 atoms per unit cell. And then carbon, where does it go? Amount of carbon, it goes into the interstitial sites, and which we will see in subsequent figures. And we also have seen defined what is isothermal transformation diagram. We explained if you have heat a steel, that is to, let us consider this for eutectoid steel, that means 0.8% carbon steel, and when you heat it above 723, this temperature is around 723 degree centigrade, say you have heated it here, and then what you do, After heating, once you know that it is homogeneous, you cool it to a particular temperature. Let us say you have a bath, say a metal bath, a molten lead bath, you have dipped it the sample and you are able to follow, say suppose you keep it for certain different lengths of time and then you quench, say one after this time, one after this time, another after this time, another after this time, and you can look at the microstructure of each of these at room temperature. What you will find that structural feature until this particular point is exactly same, so similar identical feature, but once it crosses a particular point you find that pearlite starts forming. You do not see pearlite if you quench from here, and then you start seeing pearlite from this point, amount of pearlite goes increasing with time and somewhere here it reaches 100% pearlite, and after that if you go on quenching there is no change in structure. And from this type of experiment what you can find is when you cool it at a particular temperature there is a certain amount of undercooling. Let us say this undercooling is delta T. Now, we see that for different delta T the transformation starts at a specific time and it is completed after a specific time. So, this is the start of transformation, this line represents end of transformation or completion of transformation, and if you repeat the experiment at different temperatures and join these points you find you get like this. And similarly, you will also find if you quench it further low you have a different kind. Here you start getting a different type of structure, but nevertheless here also it starts after a particular time, ends at a particular time. So, this type of C type of curve which is very similar to what you get during precipitation hardening, during quenching also we talked about this type of C shaped curve, and you must cool it faster than a critical cooling rate to get specified structure. So, there also to get a supersaturated structure. Here also we will see if you cool faster than a critical cooling rate, then here also you get a supersaturated structure, and we will know about it little detail a little later. Now, difference here is unlike precipitation hardening, this supersaturated structure is extremely hard and brittle. So, this is a basic difference between precipitation hardening and the hardening that takes place by rapid cooling in steel. And we have also defined, we have also seen that the structure that you get becomes finer as you go down. The transformation temperature goes down, structure becomes finer. Here it is a little coarse pearlite. Coarse pearlite means these lamella, these are wide apart. Whereas, if you are cooling somewhere here, these lamellae they are much finer. Sometime it may be so fine that it may appear as a dark patch in the microstructure, but at a high magnification they can be resolved, and you can see that they are also made up of alternate layers of cementite and ferrite. And as the structure becomes finer, its hardness increases. This is the hardness which is given in Rockwell C scale. And when you come here, the structural feature changes, and this type of structure is called bainite. And when you quench rapidly, it has a different types of structure. Here you are not allowing movement of carbon atom to take place. So, you get a supersaturated structure, and this structure is called Martensite. And now, let us quickly there are little differences in this. We have just seen coarse pearlite means this pearlites, they are closely, these are pearlitic structure, coarse pearlite. In fine pearlite they will be much, this plate distance, cementite to cementite plate distance will be much smaller, something like this. There will be an entire portion will be filled up if it is 0.8% carbon steel, it will be 100%. Sorry, this is the fine pearlite. We will come to this bainite little later. So, this structure actually this is where you will have very fine pearlite here. Now, bainite, we have a two distinct type of bainite. What is happening here? Your undercooling is much more. So, that means this is quite high. So, rate of nucleation will be very high, but since the temperature is low, the rate at which carbon atom can diffuse, this is low. So, the distance through which carbon atom can diffuse is will be much smaller here, and what happens, these pearlite where you have this long cementite needle, instead of that what you have broken. So, you may have this kind of a structure. These platelets, they may not be, and they will all originate from the start from nucleation from grain boundary, and they will always these plates will be very fine, and this will be impossible to see under optical microscope. So, rest of the portion, so you will have such fine broken platelets of cementite in ferrite matrix. So, this will be the structure, and since it is much finer than fine pearlite, it is stronger. And again you have another kind of bainite. Here what happens, you have some platelets of some ferrite nucleating, and then you have some types of a carbide, these are metastable carbide, these are even finer, and this type of a structure called acicular bainite. So, maybe what you see is you will have some plates of ferrite nucleating, and within this, since this carbon atoms, they form at a particular angle to the direction of this means needle like. If this is the shape of a ferrite grain, what happens, you have this carbide which are precipitated like this, and I think it was mentioned this carbide here, it is cementite, and this carbide is called epsilon carbide. And we have seen that metastable structure have different composition, different may have different crystal structures. And now, in this extreme case, when you have this Martensite, you do not allow the carbon to precipitate out. What you have, if you have these are the austenite grains, within this austenite grain you have this type of a needle type of structure forming an entire thing. They cannot cross the grain boundary, but this entire thing, these are single phase structure, they also will be their fineness will depend on how large is this austenite grain. Some of these, if grains are coarser, you can even see these needle like structure in optical microscope, and this type of structure is called Martensite, and it is there is no precipitate here. What you have is no precipitate, and this is, and here this is the type of structure on quenching which you get has maximum hardness. Say RC scale, it may be some RC 64. So, this is an extremely hard structure that you can get in the steel. Now, the question comes, why is it so hard? I mean, what happens? Where does this carbon atom go if you cool it very fast? That answer lies into the crystal structure and the atomic size of iron atom and carbon atom. And if you look back your these figures, see this is a austenite structure, you have face centered, and these are the potential sites. And if you go back to your earlier notes, how to find out the number of interstitial site, and it was shown you have one interstitial site per atom. So, you have very large number of sites available, but it will be worth looking at how many carbon atoms do you have. So, if you have all sites are accommodated, if every site if you have carbon atom, then atomic in that case percent solute will be you can go even up to 50 atomic percent, which never happens. It cannot accommodate so many, because this, if you look at the dimension of this interstitial sites, these dimension of these interstitial sites are large enough to are not large enough to accommodate carbon atom without lattice distortion. So, if you put in a carbon atom here, there will be lattice distortion, and we have seen that lattice distortion in this case is little less. I mean, it is symmetric in all direction. You look at this atom, surrounding is exactly same, surrounding of all interstitial site is exactly same. Look at the atom and the site at the center of the face centered cubic. Now, if you join these, what you get is an octahedron, 8 faces. You can join similarly the bottom, and it is possible to show, in fact, this was shown also, that the dimension, the space in all directions, in this directions the gap, in this direction the gap, they are identical. So, this is so if this carbon atom goes here, it will only have an hydrostatic stress field, whereas look at this atomic sites. So, here also carbon goes into the octahedral sites, but which is an octahedral, all these surroundings they are all same, and if you try and find out that number of atoms these interstitial sites in BCC structure, you will find there are 3 sites per iron atom. So, that means here number of atoms per unit cell of iron atom, you have 2 iron atom, whereas you can accommodate up to 6 carbon atoms. The sites are available, but the point is, if you look at this octahedron here, so best way to imagine that octahedron, here also you have similar, it will be exactly same. Say look at this octahedron, how does it, see you join these faces, they are all identical, mind you. So, this is a half octahedron, and similarly if you join this atom, that iron atom, in the next layer just above this, you will find there is an iron atom, be a center iron atom in the next neighboring unit cell, and if you join these, you get this octahedron. Now, look at this octahedron, if you have this dimension is much larger than this dimension, and this is very small, and it is so small that there will be lattice will be distorted unevenly. It will be distorted in this direction much more than this. Possibly this direction it is so large, there will not be any, rather it will try to, these atoms will try to come, can even come closer, whereas this side is less than, much less than the atomic diameter of carbon. So, this side these atoms will be pushed apart significantly, and this leads to an asymmetric lattice distortion, and which has much stronger stress field than this. It is not only hydrostatic, it will also have shear stress field. So, therefore, these type of stress field can block the dislocation motion much more effectively. Now, a point about that how many atoms or carbon atoms you have in steel. Say suppose you look at this and how do you calculate to see atom fraction of carbon in eutectoid steel. So, eutectoid steel you have 0.8% carbon. So, to convert it into atomic fraction, what you have to do, this 0.08 you multiply by atomic weight of iron divide by atomic weight of carbon. So, this, and if you do that, you will find that even in eutectoid steel you have 4 atoms of carbon, 4 carbon atom, and within say let us say roughly 100 iron atoms. So, ratio between is 4 and 100. So, even within that unit cell. So, basically what you see is if you have a face centered cubic structure, you have very large number of sites. So, question of this sites getting saturated, it does not arise. So, you have plenty of sites to accommodate carbon atom. So, carbon atoms and these and if at all a carbon atom is located here, the lattice will be distorted no doubt slightly if you keep by force I mean some amount of carbon atom, but this distortion will be uniform in all direction. So, as the carbon concentration goes in austenite, its lattice parameter will increase, but it will not the lattice will not be distorted. But what happens if you do the same thing here? What I mentioned is if you have a site here, this gap is very less. So, this will try to expand, whereas this side, this is much larger than this gap. So, therefore, what happens, this lattice, if you want to keep more amount of carbon in the lattice will get distorted. So, carbon, see 0.8% carbon is fully soluble in austenite, that is if the temperature is greater than A1 or or greater than that 723 degree centigrade. Now, imagine you have heated this to this, you have 0.8% carbon. So, here also you have plenty of sites, is much more than what you have here, but these sites are smaller. And if you are trying to keep this so many carbon atom by force, and mind you, if you have carbon, solubility in BCC is very limited 0.02. So, if you are trying to keep this much of carbon, imagine the amount of to the extent to which this lattice will get distorted, and this distortion is so large that its crystal structure also changes. It is no longer, this is BCC, ferrite is BCC, but martensite is body centered tetragonal, and often it is shown or people visualize this is a supersaturated solid solution of carbon. People often consider this as a supersaturated solid solution carbon in alpha iron, and often they write it as alpha prime. And since you have kept so many carbon atom by force, that lattice will be highly distorted, highly strained, and you have so many carbon atom in the lattice, and this carbon atom will inhibit movement of dislocation, and that is why this microstructure is extremely hard, and with this hardness it becomes brittle as well. It is hard and brittle. Now, we in fact have talked about it, this transformation diagram. Depending on that isothermal transformation, you get if you are transforming somewhere here, you get coarse pearlite structure. If you are having a transformation somewhere here or somewhere near the nose, you have very fine pearlite. Similarly, in this benitic region, if it is upper benite, you call upper benite, which is feathery, you have the broken cementite platelets, broken cementite platelets, and here you have acicular needle like structure, and within this needle you have a needle like this, and you have very fine epsilon carbide, and in case of a martensite you have full the needle like structure called martensite, and hardness goes on increasing as the structure becomes finer, and you get maximum hardness over here. Now, the question comes, so that means you can get a wide range of microstructure in the steel depending on how you allow the steel to cool. So, one can design then think of various types of isothermal heat treatment process. Suppose we say that can you design a process of heat treatment where you will get mixture of, let us say, in a eutectoid steel you get some amount of pearlite, some amount of benite, and and balance martensite. Is it possible? So, if you look at the diagram here, so then you have what you have to do, you have to maintain a bath, a number of baths at different temperatures, say one where pearlite can form, another temperature where benite can form, and another bath where you can quench. Say maybe this bath will be at a room temperature, some water bath, you just quench in water, whereas in this case you have one bath maintained at this temperature. So, this path, if you follow this path, let it remain over here, and holding time should be greater than the time at which pearlite transformation starts. It must cross this and then keep it until then you quench to another bath, and when you quench, mind you, even though it is crossing this area does not mean that benite will form, because for benite to form carbon has to diffuse, and when you are quenching you are not allowing that time. So, even though this passes, apparently it looks it is passing through this, but mind you, this is isothermal transformation diagram. It represents this C curve is unless you have a hold time here, the transformation cannot take place. So, what you do? You come over here, then you hold until benite transformation starts. So, here the benite starts, keep it for some time, then you quench, and mind you, this transformation till part is this portion is untransformed. So, then you get a mixture of you can get a mixture of pearlite, you can get benite, pearlite, benite, and also martensite needle, and this property will be, you can say, the composite type of relationship you can use, that it will depend on hardness will depend on how much pearlite, how much benite, how much martensite you have. So, this will make maximum contribution to the strength, this will make minimum, and this will have intermediate contribution. Now, a critical look at how pearlitic transformation actually takes place. Let us look at the mechanism by which pearlite forms in in a austenite matrix. Say suppose here you have an austenite grain. How does this pearlite forms? Now, for the pearlite to form, you have to give certain amount of undercooling, and this undercooling, that is delta T. So, you have to keep this steel at a temperature lower than 723 degree centigrade, And now, here the rate of nucleation depends on nucleation rate is proportional to delta T. So, nucleation is a, you can say it is a stochastic process, is probabilistic, and this is controlled by delta T. So, that means the key factor is for any nucleation process, it has to overcome an energy barrier, and we did talk about the critical energy barrier, how you find out that the free energy barrier for nucleation to take place, that is the critical that energy hump that has to be crossed, and this is proportional to delta T. So, if you have now let us say first a cementite plate nucleates. When cementite plate nucleates, if you look back at this phase diagram, say if you are looking at that eutectoid steel. So, you have come over here. Now, look at what will be the composition of cementite, now which can remain in equilibrium with ferrite. So, here you will draw a line like this. So, cementite is somewhere here 6.67. So, now the cementite concentration is 6.67, ferrite is, let us say, around or virtually 0, let us say ignore this, is virtually 0, it will be very small, it will be 0, let us say at this temperature it is 0.01. So, what happens when cementite nucleates, it will withdraw, say around it, for cementite to form you need so much of carbon content. So, if a cementite plate forms, imagine it will capture all the carbon atom from the nearing region, all carbon atom from nearing region goes here to form this cementite, say all this carbon atom from this. So, what happens in the neighboring region, carbon drops down drastically. So, let us say this carbon content is the average carbon content of the steel, 0.8% carbon. Here the carbon content goes up to 6.67. So, it comes here, then the carbon content goes up to 6.7. So, this is a platelet of cementite has nucleated. And now, once this grows to a certain point, then this carbon content decreases so much that a plate of ferrite nucleates. And when a plate of ferrite nucleates, this is cementite, this is ferrite. When a ferrite nucleates, it will reject, ferrite has hardly any carbon content, but austenite steel, here you have 0.8% carbon. So, from 0.8 it has to reject the carbon, the surrounding area has 0.8. So, if it rejects the carbon, again at the boundary, therefore, the carbon content starts building up, and this process continues. So, this is rejecting carbon, it is rejecting all carbon from ferrite comes to this region, and when it comes, and as this carbon concentration increases to 6.67, again a plate of cementite nucleates. So, that is what is happening is in the process two things are happening, this process of diffusion, say carbon moving from here to here, and carbon moving from ferrite to this place, from ferrite to here, here, and with this process these can grow in this direction, and it can, through nucleation and subsequent growth, it can grow in this direction. So, it will grow this direction as well as this direction equally, and ultimately what may happen in the microstructure, what you find, say if you have a grain of austenite, you have these pearlitic regions growing, it is growing in all directions. So, that means they will be apparently they may look like this kind of a circular thing, and here you will have different types of that arrangement of, sometime from the side also a plate can nucleate. So, this is the way, and it will ultimately you will find they will form into a nodule, and this will grow, and until after some time they will start impinging, and then the growth stops, and finally entire structure will be converted into entire 100% Pearlitic structure. So, what we say that for Pearlitic transformation to take place, we have two simultaneous things taking place. One is a nucleation, second is growth. This nucleation, it is proportional to level of undercooling, and growth is proportional or growth is a function of, is proportional to the diffusivity of carbon atom, and diffusivity we know is a strong function of temperature. Say activation energy, say this is Q over R T. So, this will depend on the diffusivity of carbon atom which diffuses much faster, interstitial atom can diffuse much faster. So, this growth will be primarily determined by the diffusivity of carbon atom, and this diffusivity, is the temperature goes down, growth becomes slower. So, that is why what happens, there is an optimum combination of nucleation and growth where the reaction is fastest, and that happens near the nose of the TTT diagram. So, this is your equilibrium A1 temperature, and we have seen this diagram is like this. So, this nose, this is the optimum combination where the nucleation and growth have optimum combination which gives fastest reaction or fastest decomposition of austenite into pearlite or through a diffusion control transformation. But if it exceeds Martensite, it is something that diffusion where we do not allow the diffusion to take place. So, that is why it is so fast, there is no C curve, you do not see anything, it is just parallel lines. This is the Martensite start temperature, this is the Martensite finish temperature, and as we go we will know that look at that kinetics of Martensitic transformation, and Martensitic transformation is called where there is no diffusion, it is a diffusion less transformation. This is a diffusion less transformation. Whereas, in case of a bainite structure, there is diffusion, but you can see in the pearlite that carbon atom moves over a large distance, and in bainite when this carbon atom does not have to move large distance. And so, that is why at a lower temperature when bainite forms, you have such finer structure, such small platelets of cementite or epsilon carbides. There the diffusion distance is much less. Now, let us look at a little detail the kinetic of Pearlitic transformation. So, we have seen that it is possible to follow the kinetics by quenching a sample say from here and cooling it at a particular temperature, some temperature, that means there is some amount of undercooling, that is delta T. You maintain this bath and you try to follow this transformation, and we have seen that transformation starts after a particular point and it is completed, starts at T s and it is completed over here. And how does this volume fraction increases with time? If you generate a plot, you get something like this, you call this fraction transformed, and if you plot this fraction transform, often you find that at a fixed temperature, that is this is constant, T is constant, isothermal means constant temperature, and here this is how the type of plot that you see. That means, initially the transformation is slow, it picks up, in between it has a maximum, then it goes like this. And what we will see, how does this take place? We have seen that there is a process of nucleation, and growth. Now, it is often natural to find out is it with some assumption, can we know or go into little depth how this type of transformation be controlled by the degree of undercooling and the transformation temperature. And that means, what you have to then know, you have to visualize or you have to imagine how the process is taking place. Now, there can be 2 or 3 distinct cases which is shown in this diagrammatically. Say suppose we can make one assumption that there is constant nucleation and growth rate, which is diagrammatically shown here, that every time at time you have certain amount of nuclei forming. So, right at say very low t, time is low, you have very small amount. So, it is close to T s, you have so many nuclei formed. Some intermediate T, what happens, the nuclei, the stable nuclei which has overcome that activation energy, they can grow. So, they have grown into this size, they have grown like this, and at the same time fresh nuclei can also form. So, fresh nuclei which are forming here. So, you have 2 parallel process taking place, that means you have nucleation, you have growth, and with very simple assumption, that means constant nucleation rate, constant growth rate, it is possible to find out what is the amount of transformation that is taken place, that is fraction transformed. Similarly, there can be another case where we can say that process takes place is first nucleation, that all the number of nucleation, there are certain specific sites where nuclei can form, and once these sites get saturated, all these nuclei have formed, then only growth can start. So, this can be one way of looking at it. So, whenever to understand any such transformation process, we do make certain assumption how this is taking place, and if we make this assumption, then derive an expression which can be connected to some of the parameters which can be measured, and then we can know, and if they are matching and if they match according with these are some derivation that you make with this, and you get one expression, the derivation, and if you make this assumption, you will get another relationship for fraction transform with the temperature and time, and then you have to match which is which represents that actual situation. Now, another thing can happen as that process continues, when f is very low, when f is nearly equal to 0, this question does not arise, that question of impingement does not arise. Now, as you can see that here this nucleation, here the question of impingement does not arise, but when it keeps growing, when it has come to grow to this level, then growth in this direction is inhibited, and ultimately what happens, then this cannot grow. So, then this will grow in other directions, this will grow, and ultimately you will have this kind of a structure. So, entire area is pearlite, let us say. So, this is pearlite nodule and this grows into these areas. So, this is an impingement effect, and how do you calculate this impingement effect? This is what we will go into. It is something like this which is shown. So, if you do not have an impingement, then you know calculation of volume fraction is quite easy. Some of this is one nucleus, this is another nucleus. Add these two volume, you get the net volume, but if it impinges, then the problem comes up. If you add the volume, so your volume fraction, if you add the two, you get a wrong amount of volume fraction, because this area or this volume you are counting twice, and we shall look at it that with this concept how it is possible to derive a definite expression for fraction transformed, say for transformations like Pearlitic transformation or any diffusion control transformation. This in fact will be even applicable to precipitation kind of transformation, and like even this type of only thing is difference is In the precipitation process in a supersaturated, the volume fraction of precipitate is very low, very small. So, the question of this impingement does not come there. So, that is, I mean, the volume fraction will be so low that impingement may not be necessary. So, with this we stop over here, and what we did today is we just revised some basic concept of phase diagram and TTT diagram. We looked back at isothermal transformation, we looked at the effect of transformation temperature on the structure, and we also tried to derive what should be the nature of martensite or what should be the crystal structure of martensite. It is distorted BCC. So, BCC, and in fact, it is called body centered tetragonal structure. We also talked at conceptually the mechanism of Pearlite transformation, where diffusion plays a very important role, and we also introduced the concept of nucleation and growth process. Thank you very much.